we appeal to the same source of inspiration that our ancients drew from, for the Western horizon. Daylight fades, dusk ends. The model proposed by the ancients to describe the observed peculiar motion of planets was, unsurprisingly, complex. In this model, the Earth was the center of revolution. In spite of its complexity, this model, a masterpiece in geometrical analysis, held sway for nearly 14 centuries among the philosophers in the Western world. During the 15th century here in India, Nilakantha Somayaji, a renowned astronomer and mathematician from Kerala, came up with a different model in which 5 of the planets known in his time revolved around the Sun, and the whole system revolved around the Earth. The Sun, the center of revolution. In this model, planets including the Earth moved in describing planetary motion. Working on precise measurements of planetary positions made by his mentor in elliptical orbits. Kepler also established a precise mathematical relation between the period of revolution of a planet and its distance from the Sun. He even imagined physical forces from the Sun driving the planets in their orbits. This time by Isaac Newton. A young Newton thought deeply. What Kepler's laws of planetary motion were a natural consequence of his newly discovered law that described bodies falling on the surface of the Earth. The planets and their satellites, comets, by Newton's mechanical clockwork universe. Newton successfully applied his newfound law to solve all the major astronomical the periodic rise and fall in the levels of large water bodies, peaking 2 times a day. This affected the tidal force of planet Jupiter on its satellite Io is so severe that Io's landmass is periodically lifted up by about 100 feet and dropped down as Io orbits Jupiter. The resulting heat melts sulfur present on Io, and it springs out like volcanic lava. Spectacularly violent tidal interactions can be seen when galaxies approach one another. Tidal force is an inescapable effect of gravity. The crowning moment for Newton's gravity came when planet Neptune was discovered. Neptune's position was precisely predicted by observing its gravitational effects on planet Uranus. So different masses accelerate when falling under gravity alone. Here is Brian Cox, noted physicist, simultaneously releasing an iron sphere and a feather. Expectedly, the massive sphere lands first. Now, all the air in the chamber is being removed. The experiment is repeated. Now the feather and the massive sphere fall at the same rate at all times. A highly counterintuitive behavior indeed inferred this profound idea by rolling spheres on an inclined plane. Gravity is from the harmful radiations coming from space. Pieces of rock from space hurtling towards the Earth mostly burn up in the atmosphere before they reach the ground and cause damage to living beings. Small or big, terrestrial or aquatic, plant or animal, all forms of life are affected by gravity. The shoot and the root of a germinating seed grow and develop in different directions in response to gravity in order to carry out their respective functions. Seeds that disperse by wind have to dilute the effects of gravity to stay afloat in air for a long time, long enough to be carried far away from one another. This is essential to avoid competition for natural resources such as light and soil nutrients. And how well they achieve this. The tiny fungus here shoots spores that move faster than a bullet fired from a shotgun. Yes, faster than a bullet. The speed and the manner of our walking or running is also influenced by gravity. On the moon, under reduced gravity, it is difficult to walk at speeds like we do so on Earth. So astronauts on the moon find hopping to be easier than walking. In the evolving story of gravity, celestial motion once again plays a pivotal role. It was observed that the orbit of planet Mercury did not close on itself. Also, the farthest point in its orbit around the Sun gets gently shifted at the end of each revolution. Taking into account the effects of all the massive bodies in the solar system, Newton's law almost fully accounted for the observed shift. Almost. But not fully. Change to explain this discrepancy. We should take a look at the new idea of gravity and how it completely explained the anomaly observed in Mercury's orbit. Realization. The happiest thought of his life, that a person falling freely experiences weightlessness. Well, if some of you are wondering if this is the shortest way to lose one's weight, please hold on. Conditions apply. You will regain all safely, of course, is one of the ways. Zooming down a steep slope in a roller coaster is another. Bungee jumping is yet another way to experience weightlessness. Space station. In this continuously free-falling system, everything is falling freely, hence weightless. So astronauts float around effortlessly. Performing somersaults is easy and safe. A drop of water or any object remains at rest, since all the objects are in free fall and experience acceleration. In all of these instances, the effect of gravity, such as weight, is momentarily nullified by going into a free fall. A rocket in space. Objects dropped by him don't seem to fall, just as in a space station. As the rocket is accelerated, he would actually tell you that the objects fell to the floor just as they fall here on Earth. A force, but one that curves space-time, a notion impossible to even imagine, and one that does not and cannot exist in Newton's framework of gravitation. Since all of us are not geniuses like Einstein was, perhaps an analogy is in order here, even if it is a crude. The stretched acrobat net here represents space-time. It is flat when there is no mass on it. Objects travel straight along expected lines. Next, the acrobat lands on the net. The net is vastly curved around him, and far away from him, it still remains nearly flat. Curves space-time. The curvature dictates the paths of light Mercury's orbit. Planet Mercury does not return to the same position after completing one revolution. This is due to the space-time curved by the sun's gravity. Thus, Einstein's new theory precisely accounted for Mercury's orbit's anomaly. Next, Einstein predicted a phenomenon that had never been observed before. That light traveling along space-time, curved by a star, would bend instead of traveling straight. The moon's shadow races across the Earth. It's about 2 p.m. local time in the island of Principe, West Africa. The dazzling sun is gradually eclipsed by the moon. The untimely appearance of stars provides a surrealistic feel. A team of astronomers photographed the starry sky around the sun. It was then compared with photographs of the same part of the sky taken a few months before and after the eclipse. The apparent shift in the positions of stars clearly indicated bending of starlight, as predicted by Einstein's theory. Distant sources pass by clusters of galaxies that are billions and trillions of times more massive than the sun. Light takes 2 or more paths in reaching us, leading to multiple images of the same object. The effect of high space-time curvature to a smaller one. This is known as gravitational redshift. Space-time curvature profoundly affects time too, of an esoteric entity that could almost freeze time for a distant observer. A long time after a star is born, there comes a time when temperature in the core is insufficient to sustain nuclear reactions. Now, gravity crunches the core, thereby increasing the temperature. This temporarily reboots the nuclear reactions in the core. Meanwhile, the astrophysicist, Professor S. Chandrasekhar, first showed that under such circumstances, gravitational collapse is inevitable. Now the mass of the core decides the final resting stage of a star. If the mass is less than 1.44 times the mass of the Sun, known as the Chandrasekhar limit, it ends up as a white dwarf. If it is more than that, but less than about 2.5 solar masses, it undergoes a series of convulsive contractions, ultimately yielding to gravity in a gigantic implosion, causing a supernova. The ejected matter contains a rich diversity of chemical elements, most of which are created in less than 1/10 of a second. Without some of these, it is impossible to think of life as we know it here. Life in all its form is the gift of gravity. What used to be the stellar core is now a super dense mass of neutrons, a neutron star. A neutron star cannot be more than 3 solar masses. If the mass of the stellar center exceeds 3 solar masses, then no known force in nature can stop complete fission. An invisible entity called a black hole. Gravity turns out to be the great dictator and images of distant stars and galaxies due to gravitational lensing. A black hole appears reddish. These unimaginable effects on light reveal a black hole lurking in the depths. It is the tidal effect on a grand scale. The in-falling matter heats up, emitting X-ray jets. Space-based X-ray telescopes such as ISRO's ASTROSAT and NASA's Chandra telescope detect such jets and thereby indirectly establishing the black holes associated with them. Nearby black thousands of years in real time. Black holes revolving around one another continuously lose energy, drawing them closer to one another. The black holes revolve with increasing speed as they are drawn closer and closer. Finally, they merge into one single black hole, whose mass is less than the mass of the 2 black holes put together. All the energy, it took 2 gigantic super-sensitive detectors, one at Livingston and the other at Hanford in the United States, to detect them for the first time, by less than the size of the nucleus of an atom. The direct detection established for the first time the reality of both gravitational waves and black holes, both doubted research institutions. Early work on black holes in the 1970s by the founding director of Jawaharlal Nehru Planetarium, Bengaluru, Professor C.V. Vishveshwara, popularly known as the Black Hole Man of India, and Professor Bala Iyer, another great general relativist and closely associated with all the activities of this planetarium, have played a key role in gravitational wave research. Since the first detection, several gravitational wave events have been detected. The merger of 2 neutron stars being a notable one. Geometric universe that lasted for 14 centuries.